I lied to you in the previous segment. I said in the previous segment that all objects with mass have a weight. And that's just not true. In fact, it's often not true. If I have a mass that is out in the depths of space, away from all other objects, it does not experience any force due to weight. So while it is true that all objects with weight have mass, not all objects with mass experience the force due to weight, because the weight force is the force due to gravity. And in order to experience a gravitational force, I have to have two bodies of mass that are close to one another. So say, for example, here's the planet Earth, and here I am standing on top of the planet Earth. I have a weight that is pulling down on me. That is Fw. I also have a mass, and then the weight is the force of attraction between that mass and the mass of the Earth. And we can calculate that weight. Fw is going to be equal to m times g. And here, g is equal to the acceleration due to gravity on the Earth, which is going to be 10 meters per second squared. If you had high school physics or high school physical science, g is sometimes given as 9.8, but we're going to use 10 just because 10 is a nice number. It's a round number. So say, for example, I have a mass that is 5 kilograms. The weight that mass experiences on the surface of the Earth is going to be equal to its mass, 5 kilograms, times g, which is 10 meters per second squared, which is equal to 50 newtons. By the way, this equation is simply an application, a specific application of Newton's second law. The next force is the normal force, and the normal force is a force that is normal to the surface, or that's really just a fancy way of saying perpendicular. The perpendicular force is simply one, if this is the surface, is going to be a force that is perpendicular to it or at 90 degrees. That's what normal means, that at an angle of 90 degrees. The normal force is often vertical, but not always. Say, for example, I have an object that's sitting on a horizontal surface. I have a weight that's acting on the object in the downward direction, and then the normal force in that action-reaction pair will be a force that is equal but opposite in direction. So it doesn't always have to be that way, because say, for example, I have an inclined plane. Here I have, this is my wife, she has a certain weight that's acting downward, and that weight is now broken into two different components. I have a component in this direction, and I have a component in this direction. So the normal force is going to be the action-reaction pair to this force. My normal force on an inclined plane, which we see right here, this is a hack squat, I think. The normal force is perpendicular to the surface, but not vertical. We can also see that sometimes the normal force is equal to the weight, but sometimes it's not. But this is a cable machine, what's this, a cable push-down machine. This is me from some years ago. I've labeled all the forces that are at work here. I have the weight that is going downward, and then I have F up. I think I had about 300 pounds on that cable, that push-down pulley machine, and I was pushing down with all 300 pounds. So the force, I have the cable that's pulling up on my hand, and then I have the weight, and then I've labeled here the normal force. That is the force that the floor is pushing up on me. And actually, I'm standing on a scale here. So normally, if I'm just standing on a scale, the normal force is equal to the weight. And in fact, that's what I have right here, that when I have a block sitting on a horizontal surface, the normal force is equal to the weight. However, in this case, I have another force, and that is the F up, that I'm pushing up, or have the cable is pulling up on me. And in this case, the normal force is not equal to the weight. In fact, if I follow Newton's second law, which says that the sum of the forces equals m times a, and in this case it's stationary, so this is equal to 0, The sum of the forces will be the normal force plus F up minus FW, and that will all equal to 0. And so if I wanted to calculate my normal force, it would be equal to, that's normal, FW minus F up. So here, for example, if I have a mass of 700 newtons and I have an upward force of, say, 50 newtons, then the scale is going to read something less than my actual weight. It's going to read 650 newtons. That is the weight minus whatever force I'm pushing up on. You can do this. Go in your bathroom scale and push downward on a surface, on the cabinet next to you, the floor, or not on the floor, but on a cabinet surface. Push down and you'll see that the weight will actually decrease. It's a good way to lose weight, by the way, if you just push down on some surface as you're standing on a bathroom scale. There are two other forces we'll come back